Here's one such attempt at chopping this program into smaller functional blocks, but by no means is it the only method of doing so. You note the use of two virtual relays, M1 and M2, and their associated instructions inside this program. The comments inform the reader that virtual relay M1 is used for continuation purposes only, and virtual relay M2 is in charge of the maintained run state. Again, we're going to use the normally closed momentary contact red push button on input 2 as our stop button, the normally open momentary contact green push button on input 3 as our maintain run button, the normally open momentary contact yellow push button on input 4 as our jog stop button, and the normally open auxiliary F1 contact of the F contactor on input 5 as a feedback input. Note Rung 1 contains a make instruction examining input I2, the normally closed momentary contact red stop push button, and a make instruction examining I3, the normally open momentary contact green run push button, in series with a coil of virtual relay M1. Virtual relay M1 is essentially a placeholder that says to be continued in later rungs. Rung 2 is our holding circuit, consisting of a make instruction examining input I5, the F1 auxiliary contact, in series with a make instruction examining virtual relay M2. Again, the comments inform the reader that virtual relay M2's function is to check whether or not the maintain run state has been asserted. Since the coil virtual relay M2 hasn't yet appeared in our ladder logic diagram, at first you might think this rung isn't doing anything, and in the deactivated state you'd be correct. However, as we complete our tour of this program, you'll see how this holding circuit check is employed in later rungs. Rung 3 is where the M1 virtual relay extension picks up where it left off. Rung 3 contains a make instruction examining virtual relay M1, and a break instruction examining input I4, the normally open momentary contact yellow jog stop push button, in series with the coil of virtual relay M2. Recall that virtual relay M2 is the maintain run state. Rung 4 contains a make instruction examining input I4, the normally open momentary contact yellow jog stop push button, in series with output Q1, the F contactor coil. Rung 5 is a parallel branch of Rung 4. It contains a make instruction examining M2, the virtual relay that governs the maintain run state, in parallel with a make instruction examining input I4 in Rung 4 above. Rung 6 and 7 serve as accessory indicator functions. When output Q1 is not asserted, output Q3, the red pilot lamp, is energized. When output Q1 is asserted, output Q4, the green pilot lamp, is energized. In summary, red light means the motor should be stopped, green light means the motor should be running. Again, you'll note that neither the e-stop nor the normally closed overload make an appearance in the program. However, these devices are readily apparent in the hardwired schematic. Wired in this fashion, the e-stop and the normally closed overload serve to override the PLC program in the event of an emergency overload event. Yes, this implementation is not pretty, but you're often forced to make unpretty compromises when subjected to cold, hard reality. Case in point, look at your lazy lab partner. I mean, be honest. Would you ever even acknowledge you know this person outside of school? No, you wouldn't. If I saw them on the side of a highway with a flaming arrow sticking out of their neck and a dog biting them in the crotch, I wouldn't even slow down. If you, however, slow down and walk through this program line by line as would a PLC during several scans, you'll note the reason behind its construction. Virtual relay M1 is merely the means of continuing Rung 1 beyond the permissible limit of 3 contact entries allowed for this particular manufacturer. Virtual relay M2 in turn dictates whether the maintained run state has been actively asserted. The holding circuit in Rung 2 is established if and only if the F contactor actually closes and the maintained run state has been asserted. Really, the business end of the whole program can be found in Rungs 4 and 5. Either the momentary contact yellow jog stop push button or the maintained run state can energize the F contactor. The primary difference being that the jog stop is momentary and the maintained run state is preserved as long as the holding circuit is established. When the program is downloaded to the target device and placed into operation, we can observe its behavior and simultaneously monitor the program using a live communications link. Note the two videos are synced up, however there's a noticeable lag in the monitoring utility. As can be expected, when the system is in the deactivated state, the F contactor coil is not energized, the F primary contacts are open, and the motor is off. Output Q1 is not asserted and the red pilot lamp is on and the green pilot lamp is off. When the green run push button on input 3 is closed, the F contactor coil is energized, the F primary contacts close, and the motor turns on. You note the coil of virtual relay M2 is energized, and when the F1 auxiliary contact confirms that the F contactor is actually closed as directed, the holding circuit is established in Rung 2. An operator can now release the run push button. When the stop button on input 2 is open, the holding circuit is broken, the F contactor coil is de-energized, and the F primary contacts open, the motor turns off. The system behaves as anticipated for the maintained run state. Let's now examine its behavior during jogging operation. When the yellow jog stop push button on input 4 is closed and momentarily held closed, the F contactor coil is energized, the F primary contacts close, and the motor turns on. You note the output Q1 is being asserted via the make instruction examining input I4 and rung 4 without the use of the M1 and M2 virtual relays. As soon as an operator releases the yellow jog stop push button, the F contactor coil is de-energized, the F primary contacts open, and the motor turns off. The system behaves as anticipated for momentary jogging operation. A spring-applied electrically released friction brake could be installed in this system to increase the accuracy of the jogging movement. Let's now examine what happens when an operator places it in the maintained run state, and then while in operation presses and momentarily holds the yellow jog stop push button before releasing it. As previously, when the green run push button on input 3 is closed, the F contactor coil is energized, the F primary contacts close, and the motor turns on. You'll note the coil of virtual relay M2 is energized, and when the F1 auxiliary contacts confirm the F contactor is actually closed as directed, the holding circuit is established. The operator can release the run push button. While in the maintained run state, when the jog stop push button on input 4 is closed, the brake instruction examining input I4 on rung 3 de-energizes the coil of virtual relay M2. However, as long as the operator keeps pressing the yellow jog stop push button, the make instruction examining input I4 on rung 4 keeps output Q1 energized, and the motor continues to spin. Outwardly, nothing has changed. Inwardly, however, the holding circuit has been broken, and the only thing that keeps this motor turning is the operator actively holding the jog stop push button closed. As soon as the operator releases the yellow jog stop push button, the F contactor coil is de-energized, the F primary contacts open, and the motor turns off. In summary, when an operator switches between the maintained run state and the momentary jogging operation on the fly, this program breaks the previously established holding circuit as intended. Note, not all jogging programs exhibit this behavior, as you'll learn in an upcoming challenge exercise. Additionally, note this implementation prevents an operator from establishing the maintained run state while the yellow jog stop push button is being actively depressed. Again, not all jogging programs exhibit this behavior, as you'll learn in an upcoming challenge exercise. Let's now examine the system's behavior during emergency stops and overloads. As previously, when an operator presses and releases the green run push button on input 3, the maintained run state is asserted. While in the maintained run state, opening the E-stop directly depowers both the field input and output devices without reliance upon any programmed instructions to do so. The F contactor coil is de-energized, the F primary contacts open, and the motor turns off. When the E-stop is reset, the system returns to the deactivated start state and does not immediately resume operation. The system seems to correctly respond to an emergency stop condition. Let's now examine this system's response to an overload event. As previously, when an operator presses and releases the green run push button on input 3, the maintained run state is asserted. If during the course of operation an overload event occurs, in this case I'm simulating an overload by manually testing it, the open overload directly depowers the affected field output device without reliance upon any programmed instructions to do so. The F contactor coil is de-energized, the F primary contacts open, and the motor turns off. Note the make instruction in examining input I5, the F1 auxiliary contact in rung 2, informs the program that the F contactor has been forced open by some outside influence and breaks the holding circuit by de-energizing virtual relay M1. Virtual relay M2 follows suit and breaks the holding circuit. As can be expected, when the overload is reclosed with the holding circuit broken, the F contactor coil does not immediately re-energize and the motor remains off. Only when the operator actively makes the decision to return the system to operation by pressing and releasing either the run or jog stop push button would it do so. The system behaves as anticipated for overload conditions. Let's now consider a scenario in which a technician purposely manually overrides the circuit by physically pushing the F contactor closed without the use of the push button station. Warning, do not try this at home. Manually overriding a motor control circuit by physically closing the contactor may not be the wisest of actions for all scenarios, especially for those systems incorporating multiple actuators. In this scenario, it is permissible to manually override this system. When a technician physically pushes the F contactor closed using an insulated tool, the F contactor physically makes connection and the motor starts as can be expected. The make instruction examining input I5, the now manually closed F1 auxiliary contact, does allow logical continuity in rung 2. However, the make instruction examining M2, also in rung 2, does not allow logical continuity and the holding circuit is not established. Despite the F contactor being held closed, the F contactor coil is not energized and only the technician's purposeful act of holding the contactor closed allows the motor to operate. As soon as the technician releases the manual override of the F contactor, the return springs open the F contactor primary contacts and the motor turns off. In summary, this particular program operates as expected during a maintain run and momentary jogging operation and can switch from run to jog on the fly. Additionally, it responds appropriately to emergency stops and overloads and will allow a technician to momentarily manually override the F contactor, but does not establish the holding circuit in doing so. Before we wrap this application exercise up and go our separate ways, realize this implementation is but one of the many different types of PLC-based unidirectional jogging circuits that can exhibit subtle and not so subtle differences in behavior. As one such example, consider the seemingly innocuous substitution of the May construction examining virtual relay M2 and Rung 2 in our existing PLC program with a May construction examining virtual relay M1. At first you might think this substitution inconsequential, but it isn't, and a very conspicuous behavioral change occurs for this modified system. If you're up to the challenge, I encourage you to investigate this modification, observe its dramatic consequences. If you need a hint, compare how our previous system responded when changing between run and jog and vice versa on the fly with this modified program's behavior for the same input scenarios. You should notice a significant change. Additionally, if you wish to keep the jogging magic alive, here's a challenge for those brave or foolish enough to attempt it. As a continuation exercise, invite the viewer to write, simulate, and test a program that would direct the operation of a PLC-based unidirectional jogging circuit that uses the maintain contact selector switch on input 1 as a mode selector. The unidirectional jogging circuit should operate as follows. When the maintain contact selector switch is in the deactivated normally open system, this system is now in the maintain run mode and will establish a holding circuit when the green start push button is pressed. In contrast, when the maintain contact selector switch is in the activated normally open held closed position, the system is in momentary jog mode and will not establish a holding circuit when the green start push button is pressed. The normally closed contact red push button on input 2 will still serve as a stop button, and the normally open momentary contact green push button on input 3 will serve as a start button. A functional program should respond appropriately to emergency stops and overload conditions. Quick programming hint for those intended to rise to this challenge. The electromechanical nature of a field input device has nothing to do with how that input can be instantiated in a PLC program. Get cracking and see if your system works as intended. You'll find this isn't as hard as you might expect, although it does take some thought and effort on your part. Take heart that you never have to rewire this PLC-based system, but rather reprogram it. Alright, that's about it for this quick application exercise. In conclusion, we programmed and tested a PLC-based unidirectional motor starter with both momentary jogging operation and a maintained run state, without the time-consuming necessity of physically rewiring the system. In the course of this application exercise, we discussed scenarios in which a program must be reformatted to fit the confines of a particular PLC. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.